This is a big train with a big task. It's carrying thousands of tons of freight.
It takes skill and forward thinking to get a heavy and valuable cargo over a mountain or across a plain. Good train crews operating big trains are using high-level skills. Those skills are called train handling. You already know how to operate a train. This video is designed to help you hone your skills and get some up-to-date research and technical information.
When you want to know more detail, you can refer to the new Pacific National Train Handling Standards.
In labs and on test tracks here and overseas, experts are looking into how trains work. They're revealing some useful information for train crews. In train operating, two sets of issues stand out: track train dynamics and fuel conservation. The first thing we should do is look at some of the forces at work in a train. Then we'll see how to control these forces to improve our operating.
When a train travels, starts or stops, there are forces pulling the train apart or pushing it together. Draft forces are the forces pulling couplings apart. Buff forces are the opposite forces. They are the compressing forces on the couplings. Draft and buff forces change greatly depending on whether the train is slowing or accelerating or going uphill or down. Controlling these forces is important, so we'll come back to them later.
Vertical force is the weight transferred to the track through the wheels. Vertical force holds the train to the tracks. Vertical force varies depending on what the train is doing.
Lateral force is the sideways force. The force pushes out on a curve through the wheels and rims. The lateral force changes greatly depending on curves and speed and so on. The LV ratio, the relationship between the downward forces and the sideward forces, is very important to the train operator. If the lateral force gets too strong, the train will derail or wear out the tracks.
Okay, we've had a look at some of the forces, but what does it mean for the train operator? Let's have a look at how these forces impact on the train and the crew. Some of the consequences of unmanaged forces can be very severe.
Let's see how excessive lateral force develops and what happens when it does. Let's say you're accelerating on a curve. High draft forces are generated. The wagons try to go straight and the lateral force pulls inward. If the draft force is too strong, the rails can turn over and the wagon falls in. This is called stringlining. Now let's look at jackknifing. Let's say you're braking on a curve. The train slows and develops high buff forces. The curve of the track means the lateral force is strong, pushing the wagons out. They derail. That's the jackknife, and it can be a disaster. Small speed increase will produce a large increase in lateral force. So, even a small overspeed can produce risks of stringlining or jackknifing or wear and tear. Lateral forces in curves play a big part in wear and tear on the equipment. A good train operator knows how to reduce damage by understanding and controlling the lateral forces involved.
Centrifugal force. When the wagons take the curve, the centrifugal force pushes the wagons out from the centre. The force is transmitted to the outside wheels, causing friction and wear. In extreme cases, it can force the rails up and derail the wagons. So, You need to manage the lateral forces on curves. High wagons or big loads make the risks larger. To combat this force, the outside rail of a curved track is usually raised. Good train operators take special care on points. There is no elevation on the outer track of points, so the lateral force can't be controlled as easily. So obeying the speed limit is very important. We've looked at some of the forces and how they play a part in the behaviour of a train. Now we're going to investigate slack. Slack is the space, the give, between the couplings of locos and wagons. On a long train, there can be up to 5 metres of slack. There can be different slack forces taking up at different times through the train, and they can have a big effect. Let's have a look at how train crews can handle slack. Controlling slack in starting and stopping is important. If you start too hard, the slack takes up at different times. It causes excessive draft forces on the couplings and can cause a breakaway. If you start hard on a curve, the draft forces can be converted to lateral forces and the result can be stringlining. So, it's best to accelerate slowly until the slack is taken up.
Reversing bunches the train and so puts a great deal of buff force into the train. If you reverse on a curve, excessive buff forces can lead to jackknifing wagons. The best way to go is to apply only enough reverse force to get the train moving, wait for the slack to take up and then accelerate.
When you start a train, the slack is taken up gradually along the line of wagons.
Sometimes when the power is on, when the slack takes up, the result will be rail burn, caused by wheel spin.
Control the slack and there'll be no spinning wheels.
Dynamic braking takes up the slack between elements of the train. Care should be taken where there are grease spots and poor adhesion areas such as wet tracks because of the risk of skidding wheels. This will concentrate extra buff forces at the head of the train and may cause the loco wheels to skid. If you brake on a curve, the buff forces can be transformed into high lateral force and that can lead to jackknife.
Knowing what type of dynamic brake you have is crucial to safe and efficient braking. Standard dynamic brakes work differently from extended range dynamic brakes. The standard dynamic brake develops maximum stopping power at 30 to 40 k's and the force reduces as the speed does. The extended range dynamic brake retains high stopping power all the way down to 10 to 13 k's. So knowing which one you're dealing with is very important. Dynamic braking will produce very high buff forces on the couplings between the loco and the first wagon. So you need to use careful modulation to avoid high lateral force that can lead to track damage or derailment. Have a look at your train handling standards for more information.
Independent braking can cause the greatest shock to the train. It concentrates forces at the head of the train, and the big buff forces can lead to wagons jumping the track.
You can use the air brakes better by understanding some basic characteristics of air brakes. Serial action is an inherent quality in air brakes. When you apply the brakes, the pressure drops in the first wagon first, and then the next, and so on, all the way down the train. So the brakes come on at slightly different times, and that can lead to large buff forces. On curves, the forces can turn into lateral forces. So what do you do?
To compensate for serial action, you use the split method of braking. The flow meter shows you how the air pressures are equalising in the train. For trains less than 1,000 metres, firstly reduce brake pipe pressure by 50 kPa and ensure a minimum total brake pipe application of 70 kPa before releasing. For trains greater than 1,000 metres, make a minimum initial brake application of 85 kPa. Then you make additional reductions until the train speed is right.
Another factor in using air brakes is the makeup of the train. Because of their lighter weight, empty wagons will stop first when the brakes are applied. If you have a mixture of empty and full wagons, you'll get different forces on the couplings and track. It's good to know the makeup of the train and to consider that in your train operating.
As you know, fuel is one of our biggest expenses. The Fuel Miser campaign aims to maintain on-time running while adhering to the principles of fuel conservation.
Train crews are involved in the Fuel Miser campaign and have come up with great techniques for conserving fuel. Managing power is one of the greatest skills of the good train operator. You can save fuel and you can reduce damage, pollution, noise and wear and tear. When we have to wait for a long time in our cars, we turn them off. We know it saves us money. The same thing applies to locos. Train operators here and overseas have found that we can save a fortune when we shut the locos down. If you're going to be waiting for more than 90 minutes, shut the unmanned locos down. In the yards, locos may not be used for a long time. If they can be shut down, a lot of fuel will be saved. Sometimes you can still save a heap of fuel by running a loco offline on trips. It depends on the load and the terrain.
Pacific National is fitting 81, 82, 90 and PL class locos with a fuel management platform that will help us measure how much fuel is being used.
In the future, these computers will provide all sorts of quality information to help us operate the train. You know, when you put your foot down, you use more fuel. In a four-wheel drive, that can be expensive. Accelerating hard in a loco is the same. It chews through much more fuel. We can apply the power efficiently using throttle modulation. We use less power to achieve the same results.
If you go straight to notch 8 on the throttle, an excess of fuel is sent to the engine. You won't get more power, but you will send out a cloud of black smoke, which is just wasted fuel.
The way to get maximum horsepower is to go one notch at a time and allow a couple of seconds for the power to build up. The result is maximum power without the black smoke. We can save hundreds of litres of fuel on a run. Our cars run better and more efficiently when they're regularly serviced. Now, we might not actually do the tune-ups, but we can help diagnose by keeping an eye on performance and reporting any problems.
The same applies to locos. Train crew can keep an eye on the diesel and watch for trouble. The sooner a problem is noticed and fixed, the better. If there is a lot of white smoke or fuel spray, the engine needs maintenance.
Everyone can contribute to the conservation of fuel, not just the train crew. Good train operating is a team effort. Though we've been looking at the technical aspects of fuel conservation, a huge amount can be done if everyone works together.
Enfield to the driver at 1511.
Driver at 1511, Enfield, over.
1511 NCD's advised of delays, require you to shut your rear engines down, over.
Driver at 1511, Enfield Yard, message received, I'll shut the rear engines down until we're due to depart, over.
This vehicle came with instructions.
We've been working with experienced train crew and other team members assembling a set of Pacific National train handling standards.
When you want more detail, that's the place to look.
When a train travels, starts or stops, there are forces pulling the train apart or pushing it together. Draft forces are the forces pulling couplings apart. Buff forces are the opposite forces. They are the compressing forces on the couplings. Vertical force is the weight transferred to the track through the wheels. Lateral force is the sideways force. It's the force that pushes out on a curve through the wheels and rims. The LV ratio, the relationship between the downward forces and the sideward forces, is very important to the train operator. Too much lateral force inwards can lead to string lining. Too much lateral force outwards can lead to jackknifing. Lateral forces in curves play a big part in wear and tear on the equipment. When the wagons take the curve, the centrifugal force pushes the wagons out from the centre. Controlling slack in starting and stopping is important. If you start too hard, the slack takes up at different times. It causes excessive draft forces on the couplings and can cause a breakaway. Reversing bunches the train and so puts a great deal of buff force into the train. Sometimes when the power is on, when the slack takes up, the result will be wheel spin. Because of the weight and power of a train, slack is important when you brake. Dynamic braking will produce very high buff forces on the couplings between the loco and the first wagon. So, you need to use careful modulation to avoid high lateral force that can lead to track damage or derailment. Independent braking can cause the greatest shock to the train. It concentrates the forces at the head of the train, and the big buff forces can lead to wagons jumping the track. Serial action is an inherent quality in air brakes. When you apply the brakes, the pressure drops in the first wagon first, and then the next one, and so on, all the way down the train.
To compensate for serial action, you use the split method of braking.
It's good to know the makeup of the train and to consider that in your train operating.
Fuel is one of the biggest expenses of Pacific National.
Managing power is one of the greatest skills of the good train operator. If you are going to be waiting for more than 90 minutes, shut the unmanned loco down. Sometimes you can still save a heap of fuel by running a loco offline. We can apply the power efficiently using throttle modulation. We use less power to achieve the same results.
Train crews can contribute to loco maintenance. Everyone can contribute to the conservation of fuel, not just the train crew. Good train operating is a team effort. See the Pacific National Train Handling Standards when you want more details.
You've seen the Fuel Miser campaign start. There'll be new technology, new training and more information. It's a big challenge and it'll require us all to pull together, but the rewards can be fantastic.